So this is what you need to do for lab credit. If you look it up at the end of part 7, it goes 9, 10, 11, 12, I think anyway. Oh, come back. Only does what you ask it to do. Does that look right? The end of part 7. Oh, it's one of those sort of days. Hi, Mike.
Hey.
12 and 25.
Thank you. I thought I was going crazy. All right, yes. So this is all for lab credit. And actually this one, kind of at a glance, it's like what's wrong with these Lewis structures, and I do have a few hints for you. So for instance, A and B, look at the pot of valence electrons, or for A. Okay, so if you take nitrogen, the pot of valence electrons, and does hydrogen want to reach out twice? I don't think so. Okay, so what's wrong with that Lewis structure? Based upon stuff we talked about. B, it's an ionic compound because calcium is a metal, so that really won't want to share electrons. See if I have any other hints for you. Down there at the bottom, and again, indicate what's wrong with this Lewis structure. I don't think that chlorine is going to form a +1 charge. Probably not. Okay. But there's those, and then there's these. Now, these are more the traditional draw the Lewis structure. So again, this is for lab credit. I would tell you, if you start down the road working these and you're like, I can't get these, well, finish working them and hand them in for lab credit. Come by and ask me, okay? So I do have some hints. You'll want these hints. For 25, I kind of, in lab, we had a central atom and then kind of went from there. Well, I kind of gave you the skeleton of some of these molecules so you know kind of how to at least get started. This is not the final Lewis structure, but for instance, for A, you can kind of see how it's connected together to the 2 middle nitrogens and then the hydrogens spreading off of that. Okay, and looks like the HOClO, I went ahead and, no, what is that? I can't read my own writing. Oh, that's D. This thing in orange is D. And the C, looks like I drew it over here. So these hints will be pushed out there. I drew these hints a year ago. That's why I'm like, she's like, doesn't she know what she drew? Well, it was a year ago. Okay? So I'll push these out there for you guys. Okay? And then down here for 28, again, you have four compounds, but you'll recognize they are ionic compounds because you see the metal, barium, sodium, magnesium, and aluminum. Okay, so I would just draw that as the cation and then focus on the polyatomic ion. Like what does hydroxide look like? Okay, what does that Lewis structure look like? What does the nitrite Lewis structure look like? What does the iodate structure look like? These are all polyatomic ions that you're supposed to know anyway. So go ahead and conjure them up out of however you need to conjure them up and draw the Lewis structure. Okay, so again, this is all for lab credit. Any questions about that? Okay, so we'll see if technology caught up. Did not catch up. So you don't need that one anymore. So we're going to go ahead and go back to the beginning of part 8. And we'll kind of cycle through part 8 and hopefully get to part 9. I really need to start lecturing on gases next week. I don't know if Monday, but definitely need to get into unit 5, which is gases. Okay. Right? So there's that slide. Okay. There's that slide. And now hopefully this slide makes a little more sense. The geometries we were talking about were structural geometries or electron pair geometries. They are all kind of about an atom. We can actually go atom by atom and then we can understand the architecture of a molecule. Okay? Otherwise known as the geometry of a molecule. Bond angles, we talked about bond angles yesterday. Orbital hybridization of an atom. Molecular polarity, that's something a little bit different, but once you have your Lewis structure, you can figure that out. Bond order, if anybody asks you what bond order is, and every once in a while I'll see this in a a Quizlet question. Bond order, this is single, this is double, or sorry, okay, single, double, triple bond. This is bond order 1, bond order 2, bond order 3. That's all it means. Okay. Oxidation numbers, we're going to get to that a little bit at the end of part 8, along with formal charges. So where I said skip, we're not going to skip now. Okay. And I actually kind of mentioned this yesterday when you guys had your triple bond. I said, does it feel like that's kind of squatty close together? Yeah. Does it feel like there's a lot of energy between those two atoms that are triply bonded together? The answer was yeah. Okay, so we're going to talk about bond properties. So assuming, we need to assume a few things. Assuming that you have the same two atoms that are bonded together, a triple bond is stronger than a double bond. Well, no duh, right? Okay, I like it when things make sense. Okay, and a double bond is stronger than a single bond. Makes sense. And so if you were to kind of put it, that's assuming that that you have the same atoms that are joined together. Now, if you're talking about the sigma bond, the primary bond, or the pi bond, the secondary bond, the pi bond is weaker than, makes sense. Your pi is weaker than your sigma. Your second to arrive is not quite as strong. Okay. So if we were going to kind of put it mathematically, we could do it this way. We could go triple bonds greater than the double bonds greater than a single bond. And so that's two carbons bonded together and a carbon-nitrogen bond together. We have to see the same trend. So here are a bunch of tables to kind of convince you of that. Okay, here we have the triple bond. If you were to cleave that, those 6 electrons that are joining those 2 carbons, it would be 837 kilojoules per mole of material that you broke. Okay, and there's the carbon and nitrogen, et cetera, et cetera, et cetera. All right, I think you don't have to take much convincing of that. And then this is the other thing I talked about. In addition to strength, we have length. A triple bond actually, it draws the atoms together. Okay, so a triple bond is shorter than a double bond, and a double bond is shorter than a single bond. Okay, so a single bond is the longest bond. Now, this one is actually changing up the atoms that are joined together. Let's just say you change up the atoms that are joined together. The larger the atom is, okay, then this makes sense. Then the bond length is gonna increase if the atom's larger. Seems reasonable. So mathematically, it kind of looks like this. With regard to length now, the triple bond is shortest, double bond, single bond, longest. Makes sense. Got some data for you here. There you go. Picometers between those cute little atoms that are joined together. And then we skip to this one. Okay, so skip a few slides, blah, 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 blah. And I'm gearing up for some more tables. So if you find this one, okay. So you recognize you recognize these 3. The SP, SP2, and SP3. They're like hopefully in your brain somewhere. Okay? So we have 2 things, 3 things, and 4 things that are scattering from that atom with regard to either sigma bonds or lone pair electrons. Okay. So SP, SP2, SP3. These over here are where you pick up a D. So these would be 5 things scattered and 6 things scattered. So this is SP3D, and this is SP3D2.
Where's this slide at? Page 6.
Thank you. Okay, and so this is like all review. We talked about, I could point to an atom, and I will on your test point to an atom in a molecule or polyatomic ion and ask you questions about that. So how many sigma bonds are extending from that nitrogen? 3. Yep. How many pairs of lone pair electrons? 1. So 3 plus 1 is 4. So what sort of orbital hybridization do we have?
Linear. No, triple.
By the way, when I say what sort of hybridization, that's the SP, SP2, or SP3.
SB2.
Why is it SP3?
Because there's 4 pairs.
Because there's 4 pairs of bonds. Yeah, there's 4 electron domains, either sigma bonds or lone pair electrons. Yep, so there's 4. So yep, so that makes it SP3 orbital hybridized. And so structural geometry? Tetrahedral, yep. Bond angle? Yep, 109.5. Very good. Okay, let's try another one. I think I must be pointing to, am I pointing to the carbon or the oxygen? Carbon. I guess I'm pointing to the carbon. Okay, so around the carbon, how many sigma bonds? 3. How many pairs of lone pair electrons? Around the carbon? None. So we're at 3. So what are we doing with regard to hybridization? SP2. Yep. And then what about geometry? Trigonal planar? Yep, I'm liking it. What about bond angle? 120. I mean, that's a good example where it looks like a 90, but no, if you were to drive a little or put the little model together, you'd see that that's swinging at 120. Very good. One more. So we'll pick on the chlorine. How many sigma bonds from the chlorine? 1. How many pairs of lone pair electrons? 3. So, of course, 1 plus 3 is 4. So what sort of hybridization has that chlorine atom undergone? SP3. Very good. And geometry? Tetrahedral. Bond angle doesn't really apply because there's not 2 atoms. But if you put 109.5, I'd go with it. Okay? Very good. So now you have this slide where I think I go from left to right and I ask you some questions. Well, no, it kind of went like this. So carbon, the nitrogen, that carbon, that oxygen. Okay, so the question here is what is the orbital hybridization and the structural geometry? So first the hybridization and then the geometry. This carbon, how many sigma bonds around this first carbon? 4. Yep, how many lone pair electrons? 0. So what sort of hybridization do we have? SP3, yep. And what is the geometry? Tetrahedral, very good. You got it. Then going on to this nitrogen, how many sigma bonds? 1 sigma bond. How many pairs of lone pair electrons? 1. So 1 plus 1, we got 2 going on. So what's the hybridization? SP, yep. And what's the shape? Linear, very good. Then on up to this carbon, how many sigma bonds? 3 lone pair electrons. It's like we're keeping score here. None. So what's its hybridization? SP2, and then what's its shape? Trigonal planar, very good. And then the last one, how about that oxygen? How many sigma bonds? 1 sigma bond. And how many pairs of lone pair electrons? 2. So 1 plus 2 is 3. So what do you think? What's its hybridization? Yep, SP2. It's the same as this one. Yep, you got it. Okay. Now this one's a little bit different. What's the bond angle? But usually I go through the same questions as I did a minute ago. So kind of going from left to right, we're going to knock out these bond angles. Now this carbon you already told me was SP3 orbital hybridized tetrahedral. So what's the bond angle? 109.5. Now we didn't knock out this carbon yet though. So what do you think? There's what, 1, 2, 3? Okay, so it must be SP2. So what's that bond angle? 120. I'm liking it. Yes, sir.
Since we'd already found out the would it be the same for the carbon?
Not necessarily, because they're 2 different. these are always questions about an atom in particular. Now, just the fact that the oxygen is bonded to the carbon, that all we cared about was that sigma bond,
Okay.
you know, and then the two lone pair electrons made it. And really can't talk about a bond angle for the oxygen because it's only bonded to one thing. So, yeah. And then, so kind of, that's a little bit related to this nitrogen. We figured out the nitrogen you guys told me was sp, and it was linear, okay? But now we're talking about the carbon, which is right next to it, which coincidentally, okay, how many sigma bonds from the carbon? Two, no lone pair electrons. So what sort of hybridization do we have? sp also. Yep. So that makes, so what's that bond angle? 180. But that's just coincidental.
Yeah.
You're like, well, it happened twice.
Yeah.
Like, no, you can't always do that, Mike. Okay, good. Did I really skip the next 4 slides? I guess I did. Must have done that twice. Okay, so on to the assignment slide. So honestly, this is for homework then. The end of part 7 is for lab credit. The end of part 8 is homework. So let's take a quick look at that. If I push the right buttons. And I found that. Okay. So for each of these, identify the central atom and propose a hybridization scheme. So say how it's hybridized. See what sort of hints I give for you. Okay, so for A, basically you have a carbon in the middle and 2 oxygens coming out. I think you got to draw the Lewis structures for these. It doesn't say draw the Lewis structure, but I don't know how you can answer it without drawing the Lewis structure. So in purple over there, I said draw Lewis structures. So draw the Lewis structure for CO2. For B, I went ahead and told you what that looks like. So for B is in red up here. So I kind of show you kind of how those atoms are arranged. And then what you need to do for B is come up with the pot of valence electrons that you have to work with to make everybody have a complete octet. That's what I kind of intended. On the test, it'll just be a central atom. Okay, it'll be more obvious. That's why I kind of want to give you hints. C should be fine, and D, don't forget, the letter D here, boron, how many electrons does it want to have? 6. So keep an eye on that for your Lewis structure. For the next one, you're dealing with NSF, like National Science Foundation. Really? No. Nitrogen, sulfur, and fluorine. Okay, so a compound that has one of each of those atoms together. So come up with the pot of valence electrons and draw the Lewis structure for that thing. Okay? And describe the hybridization of the central atom. And I'm thinking sulfur's in the middle. It must be. I didn't look at these recently, but I think it is. All right. So for number 9, it's an odd one, so you should have the answers available to you. Describe the hybridization for the chlorine in ClF3. And this is one of those where it wants more than 8 electrons. So you're going to be talking about sp3d or sp3d2. Okay, that's your hint. So 10 is another expanded valence. My advice was to draw the Lewis structures like we did in lab, though, but just know that that middle atom's going to want more than 8. It's either 10 or 12. Okay? All right. Next one looks like this. Draw the Lewis structure and describe the central carbon atom. So again, we've got an assortment of compounds here. Especially for B, I wanted to tell you how it was arranged. So I have the skeletal structure for B right here. Again, come up with a pot of valence electrons and give them all a complete octet. So that's not the final Lewis structure. You know it's not because oxygen only has, 4 and it wants 8. So that's not quite done yet. All right. Is that about it? Oh, I went ahead and for acetone. Acetone looks like this. Acetone actually has a carbon chain, 3 carbons. that has hydrogen scattering off the first carbon. The second carbon has a double bond oxygen, and the third carbon is like the first carbon. And then I went ahead and expanded what does this mean. This kind of skeletal structure, it really means, and I expanded it out here just to make sure we're all on the same page. Okay? Is there one more page of these? My goodness. Draw Lewis structure. You're going to be drawing these in your sleep. And check out individual electron pair geometries to see what the molecule is like.
It's like you randomly wake up and you draw a Lewis structure on the wall.
Yeah, it's like Lewis structure. Okay, very good. Okay. Is there more? There is more. So I must have given some hints here. So for A, I wanted to emphasize when they give you this structure, what that means is these two chlorines are kicking off of that carbon, and these two chlorines are kicking off of that carbon like this. And this structure, C, is really like this. So not bad. Okay. So, do we all find this? Okay. Now, I think some semesters I probably skip this because I think it confuses students, and I sure that's not ever my intent. We've been talking about the electron pair geometry, okay, structural geometry, related to the hybridization of a particular atom. Now this actually takes you through a series of looking at what the molecule looks like. And I really don't emphasize that this semester. But, and I do a little bit have to in general chemistry too. So for instance, if you were to draw the Lewis structure, this is the way it works. If you were to draw the Lewis structure, BeCl2, the beryllium would be in the center and your two chlorine atoms would be on either side. And it actually would look something like this, okay? I don't think that's the final Lewis structure, but they're just showing the electron domains, two extending from the beryllium atom. So it is sp orbital hybridized and linear. Okay, so this one now, okay, we have an example, BF3. So you have a central boron atom and 3 fluorine atoms. And of course boron wants only 6 electrons anyway, so it's happy there. Now of course you would say that the boron's reaching out with 3 covalent bonds. It makes it sp2 orbital hybridized, has 3 electron domains, trigonal planar. Now this is where it differs a little bit. So the molecular shape would also be trigonal planar. But let's just say we substitute one of those sigma bonds atom with a lone pair electron. Okay, an example is SO2. You evidently have a central sulfur atom, 2 oxygens, and that sulfur also has a electron domain, okay, lone pair electrons. So we would call that, we would call around that atom trigonal planar, okay, but the molecule would be bent. Okay, the molecule basically blows off this region that we count, a molecular shape. That's all that is. And so then we can actually take it through, what if you have 4 things extending from an atom? Well, if those 4 things extending from an atom are covalent bonds, you have an atom at the other end, okay, actually your molecular shape is going to match up with your structural geometry, okay? But let's just say we substitute one of those atoms. Now we don't have it bonded to an atom, but we have that electron domain occupied by a lone pair electrons. You would still tell me that atom A is tetrahedral. You would still tell me that. But now the molecular shape's different. Now the molecular shape, we basically blow off that atom up there because it's not up there anymore. The molecular shape we wouldn't call tetrahedral, we would call that trigonal pyramidal. Okay. So again, this molecular shape I'm not emphasizing right now this semester. That's probably the reason why I don't do this. Now we have one more option. Actually, a water molecule looks like this. A water molecule has an oxygen, hydrogen, hydrogen, lone pair, lone pair. You would tell me that oxygen atom you did in lab yesterday, you would tell me the shape, the electron pair geometry, the structural geometry on the oxygen atom is tetrahedral. But with regard to the molecule, I blow these off, and what I have is actually a molecular shape called bent. These are just simple molecular shapes. So that's kind of how that goes. It's really not that confusing, but I really emphasize the first column and not so much the second one. And then we take it on to expanded valences. Okay, so this is sp3d, where now we actually have 5 things. Okay, and then we said that has the trigonal bipyramidal look. Remember how the balloons had kind of 3 here and then 2 up like that? Well, if they're all occupied, all those electron domains are occupied by sigma bonds with atoms at the end, the molecular shape matches up with the structural shape we talked about. But let's go ahead and start substituting. Instead of having an atom, what if this is just a lone pair electron? Well, it would still be trigonal bipyramidal with regard to the shape around that atom A, but with regard to the molecule, it's seesaw. How cool is that? Okay, see how that works? I have a few more. Okay, so this is where now, again, sp3d. Now we're going to substitute 2 for lone pair electrons. That's a T-shaped. Although, like I said, this first column over here is telling you the structural geometry around atom A is the same. And then last but not least, is that not cool or what? Okay, so now kind of that's the skirt of 3 electron domains extending from the central atom. Now we actually have lone pair electrons. And we have now this shape is actually linear. But you would have to say around the atom it's trigonal bipyramidal. I think that's neat. And then sp3d2. So this would be an expanded valence again where the central atom has what? 12 electrons? Okay, so we call that octahedral, and if all electron domains are being occupied or participating in sigma bonds to another atom, that's the same shape as the molecule. But we can start substituting out, and that's kind of fun. That's a square pyramidal. Okay, this is a square planar. That's kind of neat. So, and I do want to take a minute and talk about this too. I'm glad I found my missing slides. Okay, so for each one of these compounds, if you drew the Lewis structures, which I think we've drawn them, you guys did water and you did ammonia in lab, and this is methane. But in each of these cases, the carbon, the nitrogen, and the oxygen, in each of those cases we have 4 things that are extending from them, whether they're sigma bonds or lone pair electrons. So 4, of course, means what? sp3. These are all sp3 orbital hybridized. So if I asked you the bond angle, it's tetrahedral, what would you say the bond angle is? Yep, 109.5. And you'd be right. You would be right. But there's a slight difference when you start substituting out. Instead of the carbon is 109.5 on the nose. But ammonia, when you start substituting sigma bond to an atom with lone pair electrons, think of those lone pair electrons as basically kind of swelling a little bit more than if it was a sigma bond and another atom. So with that, basically it kind of squeezes the legs of the ammonia. Instead of 109.5, it's 107. But you guys put 109.5, and that's great. Sometimes you'll see the approximately 109.5. For water, actually then it's got 4 electrons, or two lone pairs that are actually doing some repulsing and pushing the legs even closer. So that bond angle is even less. Squeeze. Yep. Okay, and then that's where we picked up, wasn't it? Cool. Well, I do want to talk about resonance structures right quick, and we'll hold formal charges for Monday, but there won't be another assignment. Assuming my technology works. You're like, oh, I hope your technology doesn't work. It worked. Okay. you'll do great with this resonance structures. I mean, it's stuff we've been talking about, okay? In fact, these first slides, you're like, oh my gosh, are you serious, Mrs. Snipes? We did like 10 billion times, okay? And you're gonna do another 10 billion within your homework. So for this formate molecule, we have a pot of 18 electrons to distribute. We draw the preliminary Lewis structure. It looks like this. So we have 6 shown, so 18 minus 6 is what we have to distribute. Hydrogen's done. We're going to distribute them around our oxygens. Okay, so this is what this should look like. Okay, so this is step 4, and what you guys did yesterday. Now step 5 was, if the middle atom doesn't have a complete octet, fix it. Okay, and of course carbon only has 6, and it wants 8. I talked about this before. And I think last time I went ahead and swung, once I advanced my slides, I swung like this. But you have to think of each one of those oxygens. We can actually label them, you know, isotopes. We can actually put like one isotope of oxygen there, one isotope of oxygen there, and we can know which one it swings from. So we swang from that one. So this would be your Lewis structure, right? Don't forget your brackets, polyatomic ion, put the charge outside. But what if we went ahead and swang not from the north one, but what if we swing from the east one? Is it a different structure? And then the answer is yes. You're swinging from a different oxygen. Okay? So those are 2 different structures. I know that it's like blinking, you're like, they look the same. It's almost like a Schrodinger question a little bit. Which one does it? No, I'm just kind of kidding. So those are both possible, actually. And I think on the next slide, you kind of see this double arrow. So kind of think of them as either.
Is there a different outcome?
Is there a different outcome? Sort of. Oops, sorry. Sort of. Because the one where you swing the electrons from, or let's put it this way, the one where you don't swing the electrons from, which is over here, actually, and we'll talk more about this on Monday, it runs around with a kind of partial negative charge. It's where the negative charge is residing, I guess I should say, because this is a negative minus 1 ion. And so over here it would be our north, and over there it would be our east. So it does make a difference. I'm not sure I entirely understand this, but I have a slide here. Of course we know rhinoceros are real, right? Try to say that. But dragons and unicorns are both mythical. They are, trust me. So the real deal is somewhere kind of in between them oftentimes. So I'm not sure. Yeah. Oh, I guess that actually leads to this. I guess I do buy that. If you go back to those 2 structures, you know, where we kind of had the partial negative charge on the east or the partial negative charge on the north, actually what can happen, you saw the double arrow between them, is it kind of lives somewhere kind of in between those 2. When I think of delocalization of electrons, I think of like you dislocate your shoulder, your elbow or something, I guess whatever this is. You dislocate your arm, okay? It's just kind of out there. And so delocalized electrons are just kind of, what? They're kind of floating, they're kind of sharing, they're kind of having a good time. I didn't bring in, but I'll try to remember to bring in on Monday, my benzene ring. Benzene is so fun, and it really just screams electron delocalization. Benzene is C6H6, and it's a ring. We have a lot of ring compounds. So carbon forms a ring. Got 6 carbons, go like this. Okay, hope that's 6. Yep. And then it alternates single, double, single, double. So single, double, single, double, single, double. Okay, and then my hydrogens or the hydrogens come off like this. It's kind of a pretty, it's very reactive. Okay, there's my benzene ring. Not the prettiest benzene ring I've ever drawn. Okay, but it's in resonance with this one. Goodness, that is awful. Okay, so this was single before, I'm gonna make it double. Single, double, single, double, single. Go ahead and put on my hydrogens. So those electrons, the pi electrons, I think that's what I'm gonna say, the pi electrons, the ones that aren't, connecting the nuclei, they're kind of extra anyway, they're party electrons. Okay? They kind of delocalize and they schmooze around this thing. It's like a humming sort of thing. I always think of a pop bottle kind of.
What Christmas ornaments.
Resonance. Right. I mean, that would make the best Christmas wreath. Oh my gosh. I am so down with that.
Make it like a wreath structure.
Yeah.
Like little ornaments off it. Carbon.
Kickstarter.
Magic marker on.
If we make that, can we get it for extra credit?
Oh no. No, but it'd be pretty darn cool. Okay. So these resonance structures make sense, and the two for formate made sense, but they don't always make sense. Okay. What makes sense mostly is if you get everybody complete octet. Okay. What we're talking about is swinging electrons, lone pair electrons, differently, making our double bonds at different locations, double, triple bonds. Preferably, if you end up with a charge like our formate had a negative on the oxygen, preferably that makes sense, and it does make sense. Oxygen is electronegative, so yeah. If you do end up with a Lewis structure and you try to say, does this resonance structure make sense? If you end up with a plus here and a minus there, might have done something wrong, okay? Or if you do end up that way, they should be as separated as possible. So you guys ran into this in lab where you could have swung from either the chlorine or the oxygen, and you swung from the oxygen because oxygen wanted to reach out twice. So that's a clue. Okay. So I have one more resonance structure to look at. So we could take the pot of valence electrons that are brought by the carbon and two oxygens, and we could distribute it this way. And that's the right pot distributed. A carbon has 8 electrons, oxygens have 8 electrons. Or we could do this, okay? Where does the oxygen have a complete octet? Yeah. They each have 8 electrons. Does the carbon have 8 electrons? Yeah. So if I call this one A and this one B, how many people think A looks better? I do. It just looks more stable, makes more sense. But actually, probably, you would tell me A is better because oxygen wants to reach out twice, and here we have oxygen reaching out once and 3 times. So there, according to the valence rule, that kind of throws that out. Okay. So here's an example where we would say that basically, I think the word says does not contribute. That's just to say that when O2 is floating around in this molecular form, this resonance structure does not contribute to the way O2 is. It doesn't make sense, and I think the best way is because it's not, oxygen's not reaching out what you would expect it to reach out in this neutral molecule. Very good. Well, let's stop there and leave that last little tidbit till Monday. And also, I really think Monday then we're probably going to start gases, so we don't feel so rushed. Sorry. Monday and Wednesday we'll do gases.
The homework for lab is due Monday.
Yep. Homework for lab is due Monday. Yep. We're on the downhill sweep, but keep those legs running.
Yes.
Yeah.